Hello everyone! Today we're going to prove an equation that shows up all the time in quantum mechanics and is super important for proving the Heisenberg uncertainty principle. In the last video, I mentioned that it is impossible for a machine to generate a particle that always has the exact same position and the exact same momentum every time. One of the two has to have an uncertainty. But I didn't explain why. In this video, we will prove an equation that is one important step towards proving the Heisenberg uncertainty principle. And it states that the commutator of momentum and position is always equal to negative I h bar. Where does that equation come from? Let's start now. So let's start by stating our assumptions. Number one, the commutator of two operators A and B is equal to A times B minus B times A. That's just the definition of what those brackets mean. Secondly, the momentum operator acting on the wave function is negative I h bar ddx wave function. We stated this in our previous video and it comes from quantum mechanics. I hope to make a whole video on that in the future. Finally, the position operator acting on a wave function is equal to the position times the wave function. This is just the definition of the position operator. So let's get on with the proof. Using the first assumption, the commutator of p and x acting on the wave function is equal to px minus xp acting on the wave function. Now using the distributive property, that's px wave function minus xp wave function. Now, in quantum mechanics, when you have more than one operator acting on a function, you start with the operator closest to the function and then progressively go to the left. So in the first term, let's have x operate on the wave function first to become x. And then in the second term, let's have p operate on the wave function to be negative I h bar ddx. So now if you look at the first term, you have momentum operating on two different functions. There's x and then there's the wave function psi of x. So we're going to need to do the product rule. So first, p acts on x, that's negative I h bar ddx x times the wave function. But then plus a second term where p acts on the wave function, so that's x, it's not being acted on, negative I h bar ddx psi. And again, we got that by using the product rule from calculus. Now, in that second term, we have a negative x hat times a negative thing. So the negative negative just ends up being positive. And when the x hat acts on psi, that just gives us x. So that whole second term just becomes positive xi h bar ddx psi. So considering that ddx of x is just 1, and that x times negative I h bar is just negative ix h bar, we can rewrite our equation like this. Now here's something kind of neat. The second and third terms are equal and opposite to each other. In other words, they just add to 0. So what we're left with is negative I h bar psi. So in conclusion, what we started with, the commutator of p and x acting on the wave function psi, equals negative I h bar psi. And in the previous video, I mentioned that sometimes operators will be written without the function that they're acting on. So we can write this as px commutator equals negative I h bar, which is precisely what I claimed at the beginning of the video. So there you have it, folks. If you've ever wondered why momentum and position do not commute in quantum mechanics, and why the px commutator is negative I h bar, now you know. Once again, this is one important step in proving the Heisenberg uncertainty principle, which is a fascinating phenomenon in quantum mechanics. If you want to learn more, please leave a like or subscribe to the channel so that I know that I should make more videos like this. And if you have any questions about quantum mechanics, leave a comment and I'm happy to make a video in the future answering your quantum questions. Have a great day.